All right, we'll take a look at your homework from last night. Of course, we copied out those identities one more time because we have a quiz tomorrow over those identities. So you'll need to be able to write out identities that I ask for. 4 sets of fundamental identities. Name one of the 4 groups of identities we're working on memorizing right now, Quentin. Reciprocal identities. You can give me the cosecant reciprocal identity.
Cosecant theta equals 1 over secant theta? You said cosecant. Sine theta.
Sine theta. All right, give me one of our, give me the reciprocal identity for tangent, Chris.
Tangent phi equals 1 over cotangent phi.
There we go. And give me a reciprocal identity that involves something we ain't used yet. Ethan.
Cosine.
Okay, let's do the cosine one.
Cosine theta equals 1 over secant theta.
All right, there we go. Of course, we could alternate any of those to get the other 3. What about our quotient identities? Give me one of the quotient identities, Chris.
Can I look at my paper?
Without looking. See if we can do it without looking. I'll give you a hint. The 2 quotient identities were tangent and cotangent equal to something.
Tangent gamma equals
Ethan, help.
Sine theta, or sine gamma over cosine gamma.
All right. Do you remember the other one now that we've written that one, Chris?
what's the second one, sir?
Cotangent.
Cotangent equals
Well, cotangent of what?
cotangent of what's one that we've never used? Beta
We use it.
equals cosine over secant.
All right, so memorize these 2 together. If tangent is sine over cosine, then its reciprocal cotangent will be the reciprocal, cosine over sine. So these are identical, they're just flips of each other. Okay, so that'll help you remember those. Negative angle identities. Really, you just got to remember even and odd, right? There are only 2 even functions, Quentin.
Sine and cosecant.
Those are not even, those are odd.
Secant.
Alright, cosine.
Secant and cosine. So the cosine of, let's say, negative alpha, or secant of, say, negative alpha, would equal what, Ethan?
Positive cosine of alpha.
Just cosine of alpha, or in this case,
Positive secant of alpha.
secant of alpha. Anything else, like for instance, sine of negative alpha, or cosecant of negative alpha, or cotangent of negative alpha, or tangent of negative alpha. I know I'm missing one. For all of these, what's going to end up happening here for our answer class?
Negative moves to
Negative
sine.
sine of alpha.
Right, it's as if the negative moves to the front for all of these. Whereas here, it's as if the negative just drops off. Okay, so your even functions will help you remember your negative angle identities, and everything else ends up being an odd function. And then we have 3 Pythagorean identities. We'll let Ethan go first.
Okay, I'll do the easy one. Sine squared theta plus cosine squared theta
Oh, you said beta, I'm
Yeah.
sorry.
equals 1.
All right. Chris, give me another one. Now that you've looked back, you cheater.
1 squared plus cosine squared equals sine squared
Wrong.
cosine.
Quentin.
Cosine squared beta plus sine squared beta. Wait,
Well, yeah, we could flip it, but we want a different
Oh.
one that doesn't have sine and cosine.
that's the one you did.
Yeah, it's on the board.
Tangent squared beta equals secant squared beta plus 1 squared.
Oh. Ethan.
Minus
1 plus tangent squared.
1 plus the tangent squared equals the
That's what I
secant
said,
squared.
isn't it?
No. All right, so Chris, we'll let you take the last one without looking back now.
1 plus cosecant cotangent equals.
Okay.
Am I missing something?
Yes, you are.
You said cotangent.
Oh, cotangent phi. equals cosecant squared. Oh, it's cotangent squared. And 1 squared.
Well, we don't have to do 1 squared.
And cosecant beta phi.
There we go. All right, it's painful, but we got it. 1 plus cotangent squared equals cosecant squared of whatever phi, beta, alpha, gamma, theta you want to use.
Is there any other
Right.
ones that you have told us?
There are several more I'm going to teach you, but these are the fundamental, the basic ones we have to be able to use. And those are the ones we should have used on our homework last night, page 107, numbers 8 and 14. Number 8, considerably simpler numbers than number 14. I'll give you that. Again, this is not a process you'll actually do for a quiz or test. This was simply intended to give you practice using these various fundamental trig identities. By the way, Quentin, what is an identity anyway?
The product of something equals product of another.
No. Ethan, do you remember?
Same properties.
An identity, remember, is an equation that's always true. So those equations I wrote up, again, they have equal signs in them, that made them equations, but it's an equation that's always true regardless of what you plug in for the variable. All right, so we were given cosine of tau is equal to negative 15/17, and the cosecant of tau is greater than 0. First thing I like to do is figure out what quadrant we're in. Quentin, you're in desperate need of some redemption here.
Quadrant 2.
Quadrant 2, because we know cosecant's greater than 0, which is either 1 or 2, while cosine's negative, which is 2 or 3, gotta be quadrant 2. All right, so let's list out the functions we need to find here. We need to find the sine of tau. We already have the cosine of tau. We need the tangent of tau. We need the tau, T-A-U, that's how it's spelled. Tau, not like towel, but without the ol, tau.
I hate writing tau. It's like, I just
weird.
couldn't.
I've never seen that.
In its simplest, it's a hook on the up.
Backwards T.
Yeah, it's kind of a backwards T.
When did you teach this one?
I think it popped up once before. It hasn't been often. We'll use it more as we go forward, I promise. You'll get used to tau. All right, tangent tau.
Just because y'all said something.
Cotangent tau. Let's see, secant of tau and a cosecant of tau. Now, which of these is the easiest to find? Secant, because it's just the reciprocal of the cosine class.
I beat you.
All right, but then we're going to have to use one of our fancy trig identities to solve for one of these other ones. And what's the second one that you found? Assuming you got secant first, Chris?
I didn't write off the formula, but I wrote 17 over 17 minus 15 over 17.
So what are we doing here? What are you trying to find? Sine, tangent, cotangent, or cosecant?
I found the sine first.
The sine. Okay, so what trig identity do we use to find the sine?
I don't know which one I used. That's why I need to write it out.
I know.
Yeah, that is why we need to write it out. Ethan?
Sine squared plus cosine squared, or sine squared theta.
Tau in this case.
Yeah. Plus cosine squared tau equals 1.
And the whole point of this was as you wrote them out repeatedly would help you to memorize them so you'd be ready for the quiz in our next lesson. But we're finding the sine, so let's first move over, class, the cosine squared as a negative cosine squared tau. And then let's also take the square root. So we're going to end up with the square root of 1 minus cosine squared tau. So let's start with the cosine squared tau. We know the cosine is negative 15 to 17, but if I square that, what do I end up with, anyone?
225 over 289.
289?
Right, 225 over 289. Those are numbers we memorized in Algebra 1 and Algebra 2, but it has been a while. How should I rewrite the 1 then?
289 over 289.
289, 289. We can subtract to get how many 289?
64.
64, which works out great, by the way, because we can take the square root of 64 evenly and the square root of 289 evenly. And technically it's positive negative, but that means I'm going to have to choose. Well, in quadrant 2, what should I choose?
Positive.
I should choose the positive, so evidently the sine of tau, class, is
Positive 8 over 17.
8 over 17. And hey, once we got sine, let's go ahead and get cosecant.
17 over 8.
17 over 8.
I didn't have this.
Now, I have the sine and I have the cosine. I could put those together to find the tangent or the cotangent, either one. And Quentin, which one?
Tangent.
Tangent. Using what trig identity?
Tangent squared equals secant squared minus 1.
Okay, 1 plus tangent squared tau equals secant squared tau, and then I could, as you said, put the minus 1 over here. I could find it that way. I wouldn't. That seems really hard compared to what I had in mind. I was thinking of using sine and cosine to get tangent. Is there an identity maybe that would be easier?
There obviously is.
Like one that I asked Chris a moment ago?
Sine,
Tangent.
tangent equals sine over cosine.
There we go. Tangent equals sine over cosine is going to be very helpful for me here, because if I put the sine, which is a positive 8 over 17, over the cosine, which is a negative 15 over 17, what happens to the 17s, class?
Cancel.
They're both the common denominators. They just cancel away. So what is my tangent?
8 over 15.
Negative 8 over 15, because positive divided by negative, negative. And once I got that, cotangent's easy. Negative 15 over 8. Now again, could you have found it using that method? Of course, but I like the quotient identity. Seems a lot easier than the than a second Pythagorean identity. Unless you just really like Pythagoreans because they seem really cool.
Yeah.
And you get to use your calculator. We really don't need a calculator for tangents. That's boring,
I
right?
love calculator.
Questions on this? Not so much even the answers as much as the processes. Questions?
I got the answers wrong.
Let's take a look at number 14 now. And the numbers were not quite as easy here. So where this one, we didn't need to pull a calculator at all, frankly. All of those were memorized numbers. We're going to need one here on 14.
Oh, yeah.
Given the sine of beta is negative 48 to 73. Given that the cosine of beta is greater than 0, let's start by identifying the quadrant, class.
Quadrant.
Quadrant 4. Cosine's positive, which could be 1 or 4, but sine's negative, which doesn't happen in quadrant 1. So 3 or 4, 1 and 4, quadrant 4. Let's find the cosine of beta, the tangent of beta, the cotangent of beta, the secant of beta, and the cosecant of beta. And which one do we find first, Chris?
Cosecant.
What is it?
Negative 73 over 48.
And let's go with the cosecant. What is something I can find as soon as I've found the cosecant? What trig identity involves cosecant, besides its obvious reciprocal we just used?
1 squared plus cotangent squared equals cosecant squared.
Yeah, 1 plus cotangent squared beta equals cosecant squared beta. So I could use that cosecant to find the cotangent, right? If I just move the 1 over as a negative 1 and maybe take the square root, I could say that the cotangent of beta is going to equal positive negative square root of, okay, calculators at the ready. Let's square the 73.
5329.
5,329. And let's square the 48.
2304.
2304. And by the way, you say, well, that's negative, right? But remember, when I square, it becomes a positive anyway. And how should I rewrite my 1?
2304. 2305.
Right, and so when I subtract 2,304, 2,304 from 5,329, 2,304, how many 2,304 do I get?
25.
3,025, and we'll take the square root of the 3,025, 55, and we already know the square root of the 2,304, 48. Careful, the 73 was the 5,329, and we have to choose positive or negative.
Quadrant 4 cotangent is negative.
Negative 55 to 48. By the way, once we found the cotangent, what's easy to find?
Tangent.
Tangent.
Negative 48.
But there's another thing that's easy to find if you have cotangent and you already know the sign. I could put these two together in what trig identity?
Tangent beta equals sine beta.
Let's go with the cotangent one just to mix it up.
Cotangent beta equals cosine beta over sine beta.
There we go. Cotangent beta equals cosine beta over sine beta. So the cotangent over 1 equals cosine over sine. How would I get the cosine by itself?
Alternate.
Just cross multiply,
Oh, yeah.
right? So I can take the cotangent, which is a negative 55 to 48, and I could cross multiply that by a negative 48 to 73. What will I get for the cosine?
55 over 73.
And then it's easy to get the secant.
73 over 55.
Again, not even so much interested in the answers specifically, but the processes, questions on this. All right, that brings us into the next thing in your notes, and that is simplifying a trig expression. This is more where we're going to be able to use these identities, and even more so in the days ahead, but simplifying trig expressions. We'll look at some pretty nasty looking trig expressions over the next couple of weeks, and the idea is to get them as easy and as simplistic as possible. Mathematicians are lazy, mathematicians like easy. We're going to see some things that don't look easy, but we're going to make them easy. 3 things that you're looking to do as you simplify a trig expression. Number 1, if you can make fewer terms, that would obviously simplify, right? For instance, if you look at an expression with 5 terms in it, and you could knock it down to, say, 2 or 3 terms, or even 1 term, well, that's obviously going to be simpler, isn't it? So simplifying a trig expression often involves getting fewer terms. Did you write that down?
Do what? Sorry, I was
Coloring, yeah.
I'll
Simplifying
think
a trig expression. Number 1, get fewer terms. Number 2, no fractions. Mathematicians like myself hate fractions. Now, sometimes you can't avoid them, but hey, if I can avoid fractions, if I could simplify out of fractions, that to me is a win. And then the last method of, here's the deal, a lot of what we'll do is on a calculator, right? And there's 3 easy trig functions on a calculator. Sine, cosine, tangent, the big 3. So if you've got other trig ratios that don't fit on the calculator, that makes things messy to enter. So if you can get things specifically even to sine and cosine, that's another way to simplify. Because let's face it, sine and cosine are easy. Right? They've got a well-defined domain. It's all real numbers. There's no asymptotes built into sine and cosine. Always has values between -1 and 1. Hey, I don't have to worry about infinities or massive numbers with sines and cosines. That's all happy. So sine and cosine is a good way to simplify trig expression. That's kind of where we're going to lean today in our lesson. Write this expression, if you would, on your paper. The cotangent of alpha plus the tangent of alpha. That actually doesn't look that bad. It's only 2 terms. Cotangent's a little bit, I don't like cotangent so well. It doesn't fit on the calculator too good. What we're going to do is we're going to try to take what is 2 terms and knock it down to 1 term if we can. At the very least, let's get some sines and cosines. Well, what's a way to rewrite cotangent in terms of sines and cosines?
Cosine alpha over sine alpha.
Cosine alpha over sine alpha using a quotient identity. So right below this, let's replace cotangent alpha with cosine alpha over sine alpha. What about tangent? Might as well do the same thing to tangent, right?
Sine alpha over cosine alpha.
Right, use its quotient identity, sine alpha over cosine alpha. Now the downside is I now have created fractions. But fractions can be used to our benefit because fractions can allow us to combine unlike terms together by getting a common denominator. So let's draw a big long line. What's the common denominator for these 2 fractions?
Sine alpha cosine alpha.
Sine alpha, cosine alpha. Everybody needs representation. If I had something like 3 over x plus 2 over y, we'd say the common denominator is xy. Well, it's not an x, it's a sine alpha. It's not a y, it's a cosine alpha. But both letters just multiply together in the denominator, give me a common denominator. But I can't just randomly change to sine cosine. Here I have sine, I need sine cosine. What's missing? Cosine. Just like in algebra, we would have said, again, think algebra 3 right now. That's what you're taking is algebra 3. I've got an x. I need an xy. Multiply top and bottom by y. And that would give me 3y, wouldn't it? Here we say multiply top and bottom by x to get the xy, and that would give me a positive 2x. Right? So here I'm going to multiply top and bottom by cosine alpha. And when I do cosine times cosine, cosine squared alpha. Now that means the same as cosine of alpha squared, but the way we write it, because we're too lazy to put parentheses, mathematicians have decided to say cosine squared alpha instead. Without the parentheses, it would imply the alpha is being squared. We know that's not the case. So, trying to dodge the use of parentheses, lazy mathematicians have said, let's just put a cosine squared. What about here? I've got a cosine, but I need a sine cosine. What do I need to multiply by?
Cosine.
Well, I've already got the cosine.
Sine.
I'm missing the sine, so I'm going to multiply top and bottom by sine alpha. And sine alpha times sine alpha? Sine squared alpha. Wait a second. Thoughts on that numerator? Cosine squared plus sine squared?
That's one of our
Or
functions.
Pythagorean.
Yeah.
Identity.
Yeah. What's that equal to?
1.
1. So this could then become 1 over sine alpha, cosine alpha. And we might leave our answer this way. Now, we've got a fraction, which I don't care for, but it's sine and cosine, which is easy. So on the calculator then, if I took the sine of the angle times the cosine of the angle and then just took the reciprocal of the answer, that would be easy if I knew what alpha was. Or we could look at it this way. If I have 1 over xy, we know that means 1 over x times 1 over y, correct? So I could think of this as 1 over sine times 1 over cosine. What's 1 over sine?
Sine.
What's 1 over sine?
1 over 1.
No, what is 1 over sine? Cosecant of alpha. What's 1 over cosine? Secant of alpha. 1 term instead of 2 terms. Now again, here I look at this as a disadvantage because it's hard to enter the calculator, but at least there's no fraction. It looks cool. It looks better than what we had before. We can simplify down. We can use the sines and cosines to do it. So here we used a quotient identity, a Pythagorean identity, and then if we wanted to, a pair of reciprocal identities, along with some algebra review. Write this down if you would, please. Cosine of gamma over 1 plus the sine of gamma plus the tangent of gamma. I wrote tangent of alpha in my notes. I know I meant gamma, so let's fix that. Oh, fractions. How I hate fractions. Ew.
It's nasty.
I tell you, disgusting. Unfortunately, I don't see a whole lot I can do because I said one of the ways we like to simplify is to change things to sines and cosines, and that already is sine and cosine. I mean, this is the only thing that isn't. So thoughts? Change that. Okay, so for now, hopefully only for now, we'll keep the cosine gamma over 1 plus the sine of gamma. And how could we rewrite tangent of gamma? Sit up straight, Chris. Arm off the desk behind you.
Sine gamma over cosine gamma.
Sine gamma over cosine gamma. And kind of like last time, right? I've got these 2 fractions, and gee, I'd love to add them together. But in order to add them together, of course, class, you have to have a common denominator. Well, remember, in algebra, if you had something like this, we said with polynomials, you'll either factor or group them. So that the x plus 3 is looked at as a quantity, and of course the y is one thing, so we would get y times x plus 3 for our common denominator. Well, here I don't have an x plus 3, I've got a y plus sine, or 1 plus sine. I've got not a y, but a cosine. Well, what's my common denominator going to be here, class?
Cosine times 1 plus sine.
Cosine times 1 plus sine grouped as one quantity. So, from here to here, what's got to change?
Cosine gamma.
Multiply by cosine gamma, top and bottom by cosine gamma. What does that give me in my numerator now?
Cosine squared gamma.
Cosine squared gamma. Let's go over here. I've got a cosine gamma. I need a cosine gamma times 1 plus sine gamma. What's missing?
1 plus sine gamma.
1 plus sine gamma. So what's my numerator going to become?
2 sine gamma.
Careful.
Sine gamma times 1 plus sine gamma.
Sine gamma plus what?
1 plus sine gamma.
Well, but let's distribute.
Times. Okay.
So sine times 1 is sine, sine times sine.
Sine squared gamma.
All right. Thoughts?
You can cancel. No, you can't. Take.
I see a cosine squared, and a little later on I see a plus sine squared.
Backwards forward.
Yeah, cosine squared and sine squared, anytime you see them together added, they're a 1. So together, that makes 1. Now there's still a plus sine gamma, that's not gone, but you know, it's there. All over cosine gamma times 1 plus the sine of gamma. Wait, Thoughts?
Cancel the 1 plus sign.
Yeah, this fraction bar is a grouping symbol, so it's as if this is grouped as a quantity, because it is, and this is grouped as a quantity, and a 1 plus sign on the top and a 1 plus sign on the bottom.
Cancel.
Cancel. So I'm left with now,
Going over cosine gamma.
good, not cosine gamma, that's in the denominator, 1 over cosine gamma, and, well, what's 1 over cosine?
Secant.
Secant of gamma. All of that could just become secant of gamma. It's a weird way to write secant gamma, but it's the same thing, right? They're equal, and we've simplified the trig expression. But a lot of times, as I said, starting with sines and cosines allows us to work these things through. Turn over a page to page 108 now. Let's do a few more of these together. I want you to copy down number 21 onto your paper.
21.
Number 21 on page 108. We have a secant squared alpha, or cosecant squared alpha plus secant alpha times cotangent alpha. Ethan, thoughts? What could we do here? Let's try to simplify this expression. Let's change something. There's got to be something we can change.
Yeah.
Like maybe a cotangent, for instance, could become
Cosine over sine.
cosine alpha over sine alpha. I like it. What about a secant alpha, for instance? Chris?
You said a secant alpha.
Sure.
Secant alpha can become 1 over cosine.
Yeah, it could become a 1 over cosine alpha. What about a cosecant squared alpha? Quentin? Can that turn into sine or cosine?
1 over sine alpha squared.
Good, 1 over sine squared alpha, or sine of alpha quantity squared, but the quicker way is this. Okay, so now we've made a bunch of fractions. Okay, I know I don't really like that, but you know, we may be able to save the day here. Thoughts? Algebra step?
The cosine alphas can cancel.
Yeah. So I really have a 1 over sine squared alpha plus
1 over sine squared alpha.
1 over sine of alpha. Now remember, one of our strategies is to go to as few terms as possible. 1, 2 terms. But fractions can help us to combine to a single term if I can get a common denominator. 1 over sine squared plus 1 over sine, what's the common denominator?
Sine squared.
Sine squared, right? Just like if I had a 1 over a squared plus, 7x over a. Well, because they're both in the same category, we take the biggest number of a's, right? Squared is already bigger than 1. It already includes 1. So I don't need both and say a cubed. So here, I can get a common denominator of just sine squared alpha. So from here to here, what changes, class? Nothing. So what changes up here? None. Keep the 1. From here to here, what changes?
Nothing.
Sine.
Mhm.
Sine. Oh yeah, sine.
Another sine. So of course up here I also have to multiply by
Sine alpha
sine alpha. And so what do I copy from a numerator?
plus sine alpha.
Plus sine alpha.
You can cancel a sine now.
Ooh, careful. We never cancel terms. We only cancel factors. So they were trying to bait you into it, and you fell. Don't cancel this sine with one of these, okay? In fact, there's nothing I can really cancel now, is there? Well, I'm done. It's ugly in the fact that it's still a fraction. It is at least all one term now, if that's any consolation. And the fact that it's all sine would make it easy to enter on a calculator if we knew what alpha
Will we
was.
ever deal with this and also have like an angle or something to put into it?
Primarily not, because the focus is the work. We assume you know how to type into a calculator. So we could easily say, sure, let's say alpha is 137 degrees. Okay, we could 1 plus sine 137 equals divided by sine 137 squared equal. And we could do that, but no, we don't. The main thing is the algebra work and the trig work behind it. Good question though. Any other questions on this one? Let's move on to number 17. That's kind of an unsatisfactory answer though, I'll be honest. I like easier than that. How about 17? Write this down. You got a cotangent squared theta plus cosecant squared theta minus 1. I'll say this, anytime I see multiple squared trig ratios, my brain, especially if I also see a 1 in there, my brain goes to what?
Take square root.
Pythagorean identities.
Yeah.
Because Pythagorean identities have squares and 1s in them, right? So, is there a Pythagorean identity that involves, say, a cotangent squared or a cosecant squared or a 1 or something like that?
Yes.
Which one?
1 plus cotangent squared equals cosecant squared.
All right, now here though, the key is that the 1 would have to be added to the cotangent squared, right? Though,
If you change all the signs.
If you move over the 1.
if I move the 1 over as a negative, cosecant squared minus 1 would simply equal the cotangent, right? Cotangent squared. Well, right here I've got a cosecant squared minus 1. So I could, instead of doing anything with sines and cosines, I could just replace that with cotangent squared.
So it would be 2 cotangent squared.
Boom! Nice and easy.
They're not all like that. None of them are going to be like
Not
that.
all like that, but every now and then. Now, the book didn't want you to do it this way. This is the easy way. The book wanted you to do sines and cosines. Sure, cosine squared over sine squared plus this becomes a 1 over sine squared. And the 1 could become negative sine squared over sine squared, couldn't it? So that we have a common denominator. So all over sine squared, I have a cosine squared plus 1 minus sine squared. The problem is, that's not quite Pythagorean, but it's close, isn't it? I know that sine squared plus cosine squared equals 1. You better have these memorized. Could I create like a cosine squared plus 1 or a 1 minus sine squared or something?
Yeah.
How?
So what you would, well, the sign's
Could you
negative.
just cancel the negative sine squared there?
Oh, careful. No, you can't cancel these because this is a term. Can't
I see
cancel
what
terms.
he's saying. You could have, back before you turn it into that, you could have canceled a sine squared with one of the sine squared.
Well, right here, but I made the 1 into a sine squared over sine squared so I'd have a common denominator. I did that on purpose. I wanted the common denominator.
So you want it to be, no, you couldn't.
What if I move the sine squared over? It would become,
Negative.
you mean 1 minus sine squared? And I could replace that with
Cosine squared.
cosine squared, which is going to be cosine squared plus cosine squared all over the sine squared. But what is cosine squared plus cosine squared?
Cosine squared.
2 cosine squared. And then I could at that point say, well, cosine squared over sine squared, that's cotangent squared. And I could have gone the backdoor route, which is where they wanted us to
Why
go.
would you do that, though?
I like the fast way.
Yeah, why would you do
All right,
that?
just for practice of sines and cosines, I guess. But yeah, I'm a fast way kind of guy. Let's drop down to number 22. Yeah. All right, I hope this simplifies a lot because it's really ugly.
Like me.
Like Ethan.
He didn't deny it.
He owns it, you know. You know?
Yeah, he has more pride than man. That made no sense.
All right.
That's it.
Oh yeah, that's gonna reduce nice.
You see something, Christopher. What seest thou?
Well, we don't have a
One.
tangent, but if you add the 1 squared plus, well, yeah, secant squared minus 1 equals tangent.
Good. Anytime you see a square and a 1 together, especially grouped like that, you gotta think Pythagorean. And we know that 1 plus tangent squared alpha equals secant squared alpha. So again, if you move the 1 over as a negative, you can replace all of this with a tangent squared. So let's do that in that first step. Let's keep the cosecant squared alpha for now, times cosine alpha times tangent squared alpha. And since I'll use the raised dot instead of the parentheses, one could argue we don't even need the raised dots, and they would be right. I don't have to have raised dots here. All right.
Tangent
Thoughts? What?
Tangent is sine over cosine.
Yeah, at this point I'm not seeing anything else I can really do because they're not like added together, but we could try sines and cosines, right? That's what we've been doing until the last problem. Let's go back to it. So tangent squared, you said, becomes sine squared alpha over cosine squared alpha.
The cosine squared alpha will be in the numerator.
I'm sorry?
The cosine squared alpha.
Well, this isn't a cosine square, it's just cosine.
No, I'm talking about the one you just made.
Oh, if we were to flip it in a minute. Yeah, let's not get too far ahead of ourselves. Let's do some more in the bottom. I like what you did with the tangent, calling it sine squared over cosine squared. Maybe we could also change the
cosecant squared and then the cosine.
Okay.
You'd have to do a reciprocal or something.
Right, so let's do a reciprocal then with the
So the
cosecant.
cosecant would become
1 over sine.
1 over sine squared alpha. And then the cosine, that doesn't need to be, I mean, it's already sine or cosine, right? So let's just put that cosine alpha over 1.
See, now you can cancel a lot. You can cancel the ones, cancel the cosines, cancel the sines.
I can
Oh, you
cancel
can't-
the
you
sine
can't
squared.
You can't cancel cosines.
I can cancel one of them though, right?
Yeah.
This cosine with one of these, so I still have a cosine here.
Yeah, and you can cancel the ones.
And I guess one's whatever.
And
But
it'd be 1 over cosine.
1 over cosine, right?
Yeah.
This 1 over cosine, but what is 1 over cosine?
Flip it and make it just cosine.
Ah, good. If I multiply by the reciprocal, cosine over 1, the whole thing just becomes cosine of alpha. So this whole ugly mess, very satisfactorily this time, just becomes cosine of alpha. Seem pretty straightforward? Again, it's just working through using the identities we've memorized, and it's what do you see? Kind of like in geometry, I give you a whole lot of facts and things, and you look at the proof, you're like, well, what do I see? How could I make this happen? And you may not all do it the proofs the same way. So in simplifying, you may not all do things the same way, but hopefully the more you see, the more simplified you can get, and ideally, we get as simplified as possible.
I can see how this would be probably like your favorite section in the entire book.
I really love this
You
section.
like seeing how...
I like the logical thought that goes into it. You're right. Number 28. We've got one more I want to show you here. We've got a tangent theta minus tangent theta cosine theta all over a sine theta. Let's see how simplified we can make this thing.
Why is there tangent minus tangent? Wouldn't that just be...
Well, careful. Tangent minus tangent would be 0, but tangent minus tangent cosine would not be. For instance, it's like having
order of operations, yeah.
an A minus AB all over C. Now, I could do what with the A, I suppose?
Cancel out.
Not cancel
Pull it
out,
pull it out.
factor out, right? I suppose I could factor out an A to get 1 minus B. So if I did that, I get a tangent theta times
1 minus, or 1 time. Yeah, 1 minus cosine.
1 minus cosine theta all over the sine of theta, I guess.
Yeah, but we don't have a Pythagorean.
Yeah, that's my thought. Like I would, if it were 1 minus cosine squared, I'm all over that. But it's a 1 minus cosine, which isn't Pythagorean. So let's try a different line of thought. My first thought was factor, and I'm like, actually, I don't see how that
You
helps
could
me.
turn tangents into sine over cosine.
Let's do it. Let's do sine over cosine. Minus, and then do the other sine over cosine. Times
Cosecant.
cosine over 1 all over sine.
So now you can cancel some stuff though.
I can't. I'm not sure if I want to or if I like the common denominator I've got going.
Yeah, that's true.
Cosine theta.
Yeah, so let's try that line of thought. Let's of course we've got the main fraction bar with sine theta, and then up here we've got a common denominator of cosine. And above this denominator cosine, we would write
Sine minus sine cosine.
But this is a complex fraction now, isn't it? And a complex fraction is really just a
Reciprocal.
division problem, isn't it? Right? I could multiply by the reciprocal. So if I multiply by the reciprocal,
Sin theta, sine theta minus sine theta times cosine.
how about make this a 1 over sine theta? And now we just multiply. Now, remember I said factoring out a tangent didn't do much for me. But now that I've got a sine theta in this denominator, if I also factored out now a sine theta to leave me with, in parentheses,
1 minus cosine theta.
1 minus cosine theta,
You cancel the sines.
I can cancel the factors. Remember we said we can't cancel terms, but we can cancel factors. So by factoring out the sign, I create a common factor I can cancel. And if I just multiply straight across, it's not great, but whatever. What do we end up with?
1 minus cosine over cosine.
1 minus the cosine over the cosine. It's kind of tempting to do 1 over cosine, which is secant, minus 1. That's 2 terms. This is 1 term. And if I were entering something on a calculator, that's easy to do. Not that this is impossible. That's just quicker and
Is there a
easier.
better way, or is it going to come to that answer?
This is pretty much what it's going to end up at. So, yeah.
Is there a faster way?
Not really. Yeah, it's not particularly
Very annoying.
satisfactory.
That's like very annoying.
It is, and we're going to take care of that annoyance in our next lesson, actually. So I work you to a point of annoyance, and then I help take care of the annoyance. Your homework for this evening, though, is to practice 3 of these. Page 108, numbers 18, 19, and 32. Page 108, numbers 18, 19, and 32. Don't forget there is a quiz tomorrow over the memorized identities, and I could tell as we were going through the lesson, did you notice you started remembering them better?
Yeah.
The more you use them, the better you get with them. We're going to keep using them, but they've got to be memorized before what we try to do tomorrow. So make sure you got a memorized quiz tomorrow. Have a wonderful rest of your day, and you are dismissed.